Dipole moment. Product of charge and distance between the charges. This is known as dipole moment. Mathematically, mu equals q multiplied r. Mu denotation for dipole moment. Q is the charge and r is the distance between the charges. Unit used is dBi, denoted by d. 1 dBi equals 3.34 into 10 power minus 30 coulomb meter. Applications: polarity of molecule, percent ionic character of polar molecules, and geometry of molecules. These are the applications of dipole moment. Polarity of molecules. For polar molecules, dipole moment mu is greater than 0 dBi when we calculate its dipole moment. For nonpolar molecules, the dipole moment equals 0 dBi. So this value will give us whether a molecule is polar or nonpolar. Percent ionic character. It is calculated by this relation. Percent ionic character equals dipole moment observed divided by dipole moment ionic multiplied 100. This relation gave us the percent ionic character of a polar molecule whose dipole moment is greater than 0 dBi. Now, with practicing the shape of molecule, you will be able to find whether a molecule is polar or nonpolar, its dipole moment is 0 or greater than 0. Geometry of molecules. Remember, dipole moment is a vector quantity. It is represented by a vector. For example, we have HCl molecule. Chlorine, being more electronegative, has a partial negative charge, and hydrogen has a partial positive charge. Now, this vector is represented as that it points from the positive towards the negative with a cross tail. So, dipole moment is a vector quantity. Geometry of water molecule. It is H2O. We can draw two shapes for it. One is linear, in which all the atoms are in one line. Another shape that can be drawn for it is that band shape or angular shape. Now, in water, oxygen is more electronegative with a partial negative charge, and both the hydrogens are partial positive, being less electronegative. Now, if we draw the vector representation, this is the vector in the angular form. These are those vectors. And if we draw the vectors in the linear form, they will be just like this. In the first case, the resultant vector is 0 because both the vectors are pointing in the opposite direction. In this way, if water has this shape, its dipole moment will be 0 dBi. In this case, the resultant vector is not 0. If we add these vectors according to head-to-tail rule, so drawing the first vector, you will get this. And then head-to-tail rule, drawing the second vector, you will get this representation. And the resultant vector is not 0. So here, if water has this shape, then its dipole moment will be greater than 0 dBi. If we practically measure the dipole moment of water, the dipole moment of water is 1.86 dBi. This value shows that water is polar molecule, and its shape is confirmed that it has this bend shape or V shape or angular shape. So dipole moment helps us in finding the correct geometry and polarity of a molecule. Practicing further more examples. Now these two examples, one is cis 1,2-dichloroethene and another is trans 1,2-dichloroethene. We are asked which molecule is polar and which molecule is nonpolar. If you look at the cis isomer, you will see that the two more electronegative elements are on one side and the electropositive elements are on the other side. And if we draw a sketch of this molecule, one end is positive and that end is negative, not positive, because of the two chlorine atoms to their side, and these two are partial positive. This shows that it can be represented by this vector. So this vector gives us that its resultant vector will be not 0, and this molecule is polar molecule with a dipole moment greater than 0 dBi. While on the other hand, if you look at the two chlorines, they are on the opposite side of one another, and the positive part has been trapped by them in the middle. Here you can draw one vector just like this and other vector just like this. Both vectors are in opposite direction, giving us that this molecule will give you a dipole moment of 0 dBi, and this molecule is non-polar. So you can predict by drawing these vectors on a molecular structure and will be able to give the polarity of a molecule. 3 isomers of dichlorobenzene: para-dichlorobenzene, meta-dichlorobenzene, and ortho-dichlorobenzene. This para has very less dipole moment than meta-dichlorobenzene, and this has in turn less dipole moment than ortho-dichlorobenzene. Because again, if you dissect the whole structure, both the negative charge are at the extreme end and the positive is trapped by them. So both the vectors are in opposite direction and the resultant vector will be 0. In this you can see that the negative charge has been shifted to a side, just like this. Both the chlorines and the positive charge is on the another side. So this will give us some dipole moment. If you look at the orthodichlorobenzene, the negative charge is further separated to one side. So here's the all negative charge accumulated here, and the positive charge is here. So this orthodichlorobenzene will have the greatest dipole moment compared to the metadichlorobenzene and the paradichlorobenzene in almost nonpolar, giving us zero dipole moment because of its geometry and dipole moment vectors. Looking at the ammonia example, ammonia has a dipole moment of 1.676 dBi, and now we are asked that which shape for ammonia is correct. So looking at this dipole value, dipole moment value, it shows that ammonia is a polar molecule. Now, which shape is correct for it? Again, dissect the shape into that vectors. Nitrogen is more electronegative, and all the three hydrogens are less electronegative. In this way, if you draw the vector, you will get that the vector is moving in this direction. So according to this shape, dipole moment should be greater than 0 dBi. In the next shape, this negative charge is trapped by the positive charge between them. So all the vectors are pointing in opposite directions. And this is why we will get no resultant vector for this shape. And this shape will give us that ammonia has a zero dipole moment. But if we look at the practical value, ammonia has 1.76 dipole moment, dBi of dipole moment. It means that this shape, pyramidal shape, is correct for ammonia, not the planar shape.